The fundamental theorem of algebra. Okay, this theorem says if f of x is a polynomial function of degree n is greater than or equal to 1, then f of x has exactly n zeros or roots. So this will include multiple zeros, real zeros, and complex zeros. And we'll abbreviate the fundamental theorem of algebra as FTA. So this theorem can also be stated as every polynomial function of degree n greater than or equal to 1 has at least one complex zero. Or also, every polynomial of degree n greater than or equal to 1 has n linear factors. So let's look at an example where we use this theorem. What are all the roots of x to the fifth minus x to the fourth minus 3x cubed plus 3x squared minus 4x plus 4 equals 0? Okay, so first we'll use the degree to determine the total number of roots. So the degree is 5. And so by the fundamental theorem of algebra, we have 5 roots. Then we'll use the rational root theorem to determine the possible rational roots. So we've got our constant term is 4. Its factors are plus or minus 4, plus or minus 2, plus or minus 1. The leading coefficient is 1. Its factors are positive or negative 1. So possible rational roots are plus or minus 4, plus or minus 2, plus or minus 1, because it's all of the factors of the constant term over the factors of the leading coefficient, which was positive or negative 1. Okay, then let's use Descartes' rule of signs to kind of determine the nature of the real roots. So I'm only going to look at the sign changes, positive to a negative, so I got 1, I've got a second one, I've got a third sign change, fourth sign change. So we've got 4, 2, or 0 positive real roots. Let's find f of the opposite of x. So I'm going to substitute the opposite of x in for x. So the opposite of x to the fifth minus the opposite of x to the fourth minus 3 times the opposite of x cubed plus 3 times the opposite of x squared minus 4 times the opposite of x plus 4. Simplifying, we get the opposite of x to the fifth minus x to the fourth plus 3x cubed plus 3x squared plus 4x plus 4. Let's count the sign changes. We have one here, and that's the only one. So we have one negative real root. Okay, so then let's test out some possibilities using the remainder theorem. Let's try x equals 1. So let's substitute 1 in for x. 1 to the fifth minus 1 to the fourth minus 3 1 times 1 cubed plus 3 times 1 squared minus 4 times 1 plus 4. That's 1 minus 1 minus 3 plus 3 minus 4 plus 4. That equals 0. So 1 is a root. So let's use synthetic division. So the coefficients of the original polynomial are 1, negative 1, negative 3, 3, negative 4, 4. We're going to divide it by 1, x minus 1. Bring down the first one. 1 times 1 is 1. Add negative 1 and 1, we get 0. 1 times 0 is 0. Add negative 3 and 0, we get negative 3. Multiply 1 times negative 3, we get negative 3. Add 3 and negative 3, we get 0. 1 times 0 is 0. Negative 4 plus 0 is negative 4. 1 times negative 4 is negative 4. And add 4 and negative 4, we get 0. So we now have a linear factor of x minus 1. And we also have the factor x to the fourth minus 3x squared minus 4. Okay, so let's repeat steps 4 and 5. So we need to find some more rational factors of x to the fourth minus 3x squared minus 4. So let's try x equals 2. If we substitute 2 in for x in x to the 4th minus 3x squared minus 4, we get 2 to the 4th minus 3 times 2 squared minus 4, or 16 minus 12 minus 4, which is 0. So 2 is a root. Okay, so let's divide. So here's the polynomial we're dividing. X to the 4th minus 3x squared minus 4. We'll use synthetic division. We need to put in our 0 placeholders. So 1x to the 4th, 0x cubed, negative 3x squared, 0x minus 4. We've got our root or 0 of 2. Bring down the 1. 2 times 1 is 2. Add 0 and 2 is 2. 2 times 2 is 4. Negative 3 plus 4 is 1. 2 times 1 is 2. Add 0 and 2 and get 2. 2 times 2 is 4. Add negative 4 and 4 and get 0. So we already had the linear factor of x minus 1. Now we have the linear factor x minus 2 and the other factor of x cubed plus 2x squared plus x cubed plus 2x squared plus x plus 2. So we need to keep factoring x cubed plus 2x squared plus x plus 2. We could do factoring by grouping. I'm just going to keep trying what we're doing. Let's try x equals negative 1. That was another one of our possible rational roots. Substituting negative 1 in for x into this polynomial, we have negative 1 cubed plus 2 times negative 1 squared plus negative 1 plus 2, or negative 1 plus 2 minus 1 plus 2, that's 4. So negative 1 is not a root. Let's try x equals negative 2 because we know we have at least one, or we have one negative real root. So substituting negative 2 in, we have negative 2 cubed plus 2 times negative 2 squared plus negative 2 plus 2. That's negative 8 plus 8 minus 2 plus 2, which is 0. So negative 2 is a root. Let's continue because now we need to divide. So the coefficients of our polynomial are 1, 2, 1, 2. We're dividing by the root, which is negative 2. Bring down the 1. Negative 2 times 1 is negative 2. Add 2 and negative 2, we've got 0. Negative 2 times 0 is 0. 1 plus 0 is 0. Negative 2 times 1 is negative 2. 2 times negative 2 is 0. So we already had the linear factor x minus 1 and the linear factor x minus 2. Now we also have the linear factor x plus 2 and the polynomial x squared plus 1. Okay, so we need to keep factoring the x squared plus 1 polynomial. I'm going to set it equal to 0 and solve for x. So if I subtract 1 because there's no b term, x squared equals negative 1. Square root both sides, we get x equals plus or minus the square root of negative 1. And remember, the square root of negative 1 is I. So this means x equals positive or negative I. We could have also tried to factor or use the quadratic formula to find the other roots or zeros here. So our original polynomial, x to the 5th minus x to the 4th plus 3x cubed plus 3x squared minus 4x plus 4 factors to x minus 1 times x minus 2 times x plus 2 times x minus I times x plus I. And its roots are 1, 2, negative 2, I, and negative I. So we know that we've got the conjugate pairs I and negative I. We had the one negative real root. We have two positive real roots. So we have 5 linear factors and 5 roots for our original polynomial function.